Okay, morning everybody. Welcome back. Isn't it great to be back? Having done exams and things and got some coursework out of the way. If you remember, we were talking about modes of corrosion, and we'd gone through from uniform corrosion, where you get an even gradual loss of cross-section thickness, to looking at some forms of localized corrosion, where you get increased attack in some particular area of the component, in the case of galvanic corrosion, in the more active material closest to the cathode material. And the reason for that is that there is a, if you like, a resistance to current flow. So the bulk of the current will flow to the nearest point, and so you get the most of the corrosion closest to the cathode. And then we looked at some other mechanisms, crevice corrosion, where you've got a pre-existing geometry, pitting corrosion, where you have quite often oxygen differential or some coating effect that localizes the attack to a particular area on the surface. And we whizzed through and looked at the effect of fluid flow to say initially you get refreshment in systems which increase the corrosion, because you've got this effect where you've got an electrode surface or an anode surface, and you want reactants to go to that surface and react to produce metal ions, and you want those metal ions to be washed away from that surface afterwards. And in a stagnant solution, everything is diffusion controlled, so it's diffusion limited and therefore a little bit slower. In a flowing solution, you get rid of that diffusion limit and it's a bit faster. Sorry, I'm standing in front of your swipe. You'll need to swipe. Under flowing conditions, the corrosion rate is a bit faster, and if the flow is actually impinging on the surface of the anode, so instead of just being a flow past it, parallel to the surface, if it's actually impinging on the surface in some way, either directly onto it in terms of flow, or because it's a pipe and it's got a bend in it, and then you get impingement on this surface here, or because you've got a defect in the pipe, like the root of a weld, that causes some turbulence, then you would get an impingement in these places here. Then it's possible to get mechanical erosion of the material as well as corrosion occurring. So you get accelerated attack because you've got a combination now of the mechanical and corrosive effects. And the extreme case of that is at very high velocities in rotors, whether they're propellers or pump rotors or other situations where you essentially run the rotors faster than you should. You can get cavitation, which is the explosive collapse of voids in the solution. So the velocity of the impeller creates a shear stress between it and the liquid. That generates voids, and they can explosively collapse. Okay, it's not bubbles, but voids in the structure. Okay. This is all coming back to you, isn't it? Yes, good. I know you've wiped it from your mind for a while because you were doing other modules, but I thought it was worth just summarising where we were. And then finally we started talking about the combination of applied or residual stresses and corrosion. And we identified that if you apply a stress to a component in a suitable environment, and there are quite a lot of environments that will give rise to stress corrosion or corrosion fatigue, then you'll get crack growth in the material. So we've got material here, we get a crack growing through the material, and that crack will grow at right angles to the loading direction. Okay, so the growth of the crack is always at right angles to the loading direction. And in stress corrosion cracking, there are two possibilities. You can either have a straight crack like this, which is a transgranular crack, often called TG, or you might get a crack that goes along grain boundaries in the material, and that would be called IG, intergranular. And quite often an intergranular crack will be branching. Okay, so this one here is an intergranular crack that they're showing, because it's gone round the grain boundaries. So there's a grain in here, and there's another one here, and there's another one there. Yeah, and the crack's gone along the grain boundaries, because the grain boundary is the most reactive part of the microstructure. So, is it transgranular or is it intergranular? Has it gone straight through the grains or around the edges? And then we were finished off by talking about corrosion fatigue, and I started by again the crack grows at right angles to the loading direction, but we talked quite a bit about this, but I'll just finish off that section, and then we'll talk about hydrogen-induced cracking, which actually isn't a form of corrosion. One final thing that you have seen before, but I'll show it to you again. It's worth mentioning that the mechanisms that we're talking about from the research or pure side, it's easy to categorise. There's this mechanism, there's this mechanism. In reality, when you're in service conditions, you might get a bit of pitting to start with, and then it might turn into cracking, or you might get a bit of one mechanism and it changes to another. And so it's a bit more complicated when you're looking at real failures to determine the mechanism. It isn't always one mechanism. And so you end up with figures like this that indicate that there is some overlap between one mechanism and another. In this case, what they've done is they've gone from static loading to cyclic loading and said, right, there's some sort of grey boundary between stress corrosion cracking and corrosion fatigue as you begin to move from static stress to cyclic stress. This boundary I'm not very happy with, as we'll see in a minute or two. Stress corrosion and corrosion fatigue are both anodic processes. They're both corrosion processes. Hydrogen embrittlement isn't. If anything, it's a cathodic process. So how they feel that there's an overlap between the two processes is a little bit of a mystery to me. You just, some of the literature isn't quite as good as you might want it to be. Right. Okay, so that's where we were. The other thing to say, while I remember, is just on timetabling. We're here today. Next week we're going to Cassie Building, and then we'll be at Cassie Building for the rest of the next 6 weeks, and then we're finished. So I finished teaching about halfway through this semester. So if you've got questions for me about anything, you need to start thinking of them. I'm happy to talk to you about anything on corrosion that I know something about. If I don't know about it, I'll tell you. And then in week 27, which is March, Dr. Narakon Suril is going to do his bit. as a sort of as afternoon blocks for a couple of weeks. So he's going to do sort of 6 hours and 2 3-hour chunks, and that will clear everything off by the middle of March, which means you've got plenty of revision time, and you can go through the past papers and send us emails about things. And it's a lovely, easy module. This, and in that sense, we've deliberately tried to make it not too intensive, so we can pick these things out. Okay. This you have seen before, but it's just to remind you, cyclic loading will cause work hardening of material and may cause it to crack, and that's called fatigue. And fatigue has some particular characteristics. So in steels, you find that there's a threshold limit below which the material doesn't crack, and that's called the fatigue limit. So that's very useful for design purposes, as long as you remember that the total stress on the material is the sum of the residual stresses in the material plus the applied stresses. Okay. It's not always just the applied stress. You've got to think about how has the component been manufactured. Does it have any additional residual stresses in it? And are any of them tensile? When you get a component that is has a residual stress in it, there's always a balance. The component is stable, it's not moving. You made a pipe, it doesn't change shape. And that's because wherever there's a tensile residual stress, there'll be an equal and opposite compressive residual stress somewhere else. And that balances the shape. And that stress can be anything up to the yield strength. So obviously if it's above the yield strength, the material will move and change shape again. And that happens in quite a lot of structures. It's the sort of thing that happens in welding ship plate. So if you have a look at a big ship, you'll see that all the panels are slightly bowed because they've been welded around the edges, and the stresses have risen to the point where it actually changes the panel from a flat sheet to a bowed sheet. So you've got a residual stress that may be as large as approaching the yield strength, and then you've got an applied stress on top, whatever that mechanical loading is. When you get corrosion fatigue, when you're actually exposed to a mildly corrosive environment, then your fatigue limit disappears, which means all your design factors, all the guys sitting in the office with the finite element analysis might as well go home. Okay. They don't have the solution, because you can't really model this, you have to test for it. And the bad news is that you have to test for it. It'll do its bit. You have to test for it at the correct frequency, at the correct loading level. You've had this one before as well, if you remember. Maybe. No. So you can't just do an accelerated test at a higher frequency. You can do that for net fatigue, for an inert environment, that's fine. But you can't do it for corrosion fatigue, because in the environment, in the solution, the crack is opening and closing. And the amount of solution going into the crack and the ejection of the solution as it closes has an effect on the corrosion rate. So you can't do it fast, you don't get the same fluid dynamics. So you have to test the material at the same speed as it's going to experience in real application. And quite often that's something like a marine environment, and the frequencies are something like 0.1, 0.01 hertz. They're quite low frequencies. So the testing takes time. If you ever get the opportunity to make management decisions about corrosion testing, and anybody comes to you and says, I'd like to do some fatigue tests, corrosion fatigue tests, say no. Because the bill will just, and the length of time for the testing is enormous. Okay, it's expensive stuff to do because you can't do it quickly. Conversely, if you're a researcher and you want to get a nice big contract, what you do is you volunteer to do corrosion fatigue tests, and you end up with a big project. So, anyway, so it's all about the solution flow in the crack, okay? Because the crack is going to open, the solution's going to go in, it's going to cause some corrosion, and then the crack's going to close and the solution's going to be ejected. Maybe not all of it, maybe the crack is still open slightly at the bottom end of the cycle, maybe it's doing that rather than, might not be hitting closed, depends on the application. But the solution flow has an influence, and therefore the frequency has an influence. And the waveform, in fact, the rise time, how quickly the crack opens, has a value, an effect as well. And this is the ratio of the min to maximum stress, and is about whether that crack's actually closing or whether it's just doing that. Okay. So I think you've had that as well, and I think that's maybe the last slide that you had. Yeah, yeah. So that really just says in longer words what I've just discussed, which is you've got to remember that for corrosion fatigue, the solution refreshment is important, whereas in air fatigue, it's not critical. So you can do accelerated tests in air fatigue. Okay. Not sure. I don't think you've had this one there. No? Good. Okay. For cracks to develop, you need some initiation points, some stress concentration. And that quite often in a corrosive environment is where there's a pit formed. So you don't have to have a corrosive pit, but it is one form of stress concentration. And the pit, when it initially grows and there's no stress effect on it, it will grow hemispherically. That's not quite a hemisphere, is it? Let's try that again. That's better. And then once it begins to notice the environment around it, there's a possibility for it to start to change in aspect ratio and elongate in response to the stress, which again is right angles, and eventually to form a crack. doesn't have to be a pit. If you've got a stress concentration because, I don't know, there's a shoulder on the component machined, maybe this is some sort of rotating shaft and somebody's machined a step in it, this will be a stress concentration. You just need somewhere for the stress to be focused. And then you'll start to get some corrosion, and then you'll start to get some cracking. So it's a little bit like the stress corrosion story. I'm hesitating for a minute. There is undoubtedly lots of evidence that you get stress corrosion cracks without any pits forming first, and there's also situations where you get pits formed and then you get stress corrosion cracks from them. That's quite easy to observe, and partially that's because the cracks tend to be pretty hairline, pretty thin cracks. In corrosion fatigue, it's a bit more difficult to decide. There's a lot more corrosion and mess in the samples. I would say, and maybe it's just a gut feeling, I'm not sure whether I've got any evidence for it, that you more commonly get pitting and then a fatigue crack in corrosion fatigue, whereas in stress corrosion you quite often get no pitting and you get a crack. So there's a slight difference in the mechanism in that sense. However, just like stress corrosion cracking, ultimately the anodic corrosion at the bottom here is all driven by oxygen differential. So you've got low oxygen concentration here, high oxygen concentration out on the surface. This is your cathode process, oxygen reduction. This is your anode process, corrosion of the steel. So they're very similar in that sense. One of the big things in fatigue is crack initiation time. Quite often, if the stresses are low in fatigue, you have a long initiation time before anything happens. And then if it does start to crack, the life of the component is relatively short afterwards. So 80% or so of the total life of the component may be building up slip damage in the microstructure for ordinary fatigue. For corrosion fatigue, that initiation time is significantly reduced because you're beginning to enhance the stress concentration on the surface by the corrosion effect. So in this case, the life of the component is going to be a lot shorter than the life under air fatigue, because the crack starts early. Right, now that tells me, I think, let's have a look at the next one. Yeah, that's okay. Before we look at the hydrogen embrittlement, which is the non-corrosion mechanism, I just wanted to say something about the corrosion we've observed so far for stress corrosion cracking, corrosion fatigue, galvanic corrosion, crevice corrosion, pitting corrosion, and so on. And all these corrosion mechanisms obey Faraday's law of electrolysis, which says Q equals ZFN. And you've probably seen this before. Sometimes the people say Q equals NFN, doesn't really matter, as long as you've got the idea that the N or the Z is the number of electrons involved in the reaction that you consider. Yeah.
Is it a positive value or negative value?
It's always a positive value. We're going to predominantly be thinking about iron, which is the main part of steel, and that's going to go to well, there are two options. Well, there are two main options: iron 2 plus 2 electrons, in which case Z equals 2. And sometimes it reacts, if the environment is right, to form iron 3 plus 3 electrons, and then Z equals 3. It's always a positive value, and you've just got to look at the anode reaction and decide how many electrons are involved in that anode reaction. So for aluminium goes to aluminium 3 plus, so the Z equals 3. I've rounded this value off. It's actually 96486, but it's quite often just rounded off to 500 for convenience. And then what this equation does is it allows us to quantify the amount of corrosion that's occurring. Because Q is the charge and equals the current times the time. So if you can measure the current flow through your component, you can work out the amount of charge that's gone through the component, and that tells you, using that equation, it's going to tell you how much of the iron has reacted. So if you can monitor the current through your system, which you can't always do, then you've got a direct handle on the amount of corrosion that's occurred, the number of moles of material reacted. Easy in the lab, but slightly more difficult looking. I'll show you. I've got it somewhere. I'll just show you this. You don't need the details at all, just to let you see something different. So first sight, this looks pretty horrible, but there we go, that's better. This is just a chart of all the different types of rust you can get, okay, for iron. And what it is a plot of the ratio of how much iron 3 plus there is generated against the total amount of oxidized material. So at this end, we've only got iron 2 plus, so FeO at this end. At this end, we've only got iron 3 plus. And you not only end up with a range of oxides, Fe3O4 magnetite we've talked about, Fe2O3, which is our common rust, is almost all iron 3. But you then also, depending on the pH, end up with a range of oxyhydroxides and hydroxides, which help the sort of next stage of the hydration of the oxides, and you get different colours, which is quite useful as well for identification purposes. So we've got our sort of reddy brown rust here, we've got black magnetite, and then we've got green rust over in the at the more iron 2 end of the process. And the squares and boxes and so on are to indicate different phases with different crystalline properties, so that you can actually analyse them as well. So, as I say, I don't expect you to remember any of that, other than to remember that iron's one of these materials that has 2 oxidation states, and quite often you end up with a mixed oxide, like magnetite, Fe3O4, which is a mixture of iron 2 and iron 3. And maybe one day when you're looking at a failure somewhere and you look at the colour of the sludge, you might think, that means it's this end or that end or somewhere in the middle. Right. Okay, so in some cases, Z is 2 for iron. Not always, sometimes it's 3. So you have to go back to your periodic table of the elements to get the relative atomic masses, what used to be called the atomic weight for a particular element. For steel, which is predominantly made of iron, we can use the value 56, but zinc in a galvanic couple obviously has a different value and so on. So you'd look up the value on any periodic table that give you the relative atomic mass. And then we can work out how long it will take in this situation to dissolve away 56 grams of the iron. As it turns out in this example, 56 grams of iron, the relative atomic mass is 56 as well, which means that this is 1 mole of iron atoms which are being corroded away. And a mole of atoms, if you remember Avogadro's number, is 6 times 10 to the 23 atoms. So we know exactly how much has been corroded away because we know what molar quantity of materials being dissolved away. So that's okay. Yeah.
Is it mass over relative atomic mass, or it's the other way?
Yeah. Yeah. It's whatever mass you've got divided by the relative atomic mass. Yeah, that's true. It's not obvious from that, is it? So if I had 100 grams of iron, I wanted to know how long it would take, it would be 100 over 56. Yeah. So, I don't think anybody's ever asked that before. I should make a note. I'll change the example. Okay. What we really want to know for a structure is about the loss of through-section thickness. When is the hull of the ship going to get too thin for it to safely operate? When is the pipe wall going to get too thin, and so on? So we need to start thinking about introducing some information about the surface area of the anode and working out the volume of material lost. And the volume relates to the mass divided by the density. So if we've got the mass, which we have from our Faraday law calculation, then given the density of the material, we can back calculate. And again, iron is the predominant component of steel, so we'll take the density of iron, which you can look up in tables, and it's 7.8 grams per cubic centimetre. And this is also, we can get, ultimately start thinking about corrosion rates, which are often defined as millimetres per year, MP1. Not to be confused with the American milli-inches per year. So, we're dealing in the surface of the structure, how much of it is in contact with the solution. So, we're having an electrode that has a 1 square metre surface area. And if we worked out the volume of material that we're losing, then the depth must be that we're losing is really very little. So you've got something that's a square metre, 1 metre by 1 metre, and the amount we're losing is a tiny little bit. Tiny little bit off that cake, which is however many microns, 7 microns. And if you take 7.2 micron, multiply it by 1, you get the total volume, 7.2 cubic
So it's
centimetres. Yep.
56 hours we're losing this thickness here.
You're losing this thickness here for an electrode of that surface area if the, let's go back, if you're, and that's equivalent to 56 grams of material, or in fact 53.6 hours at 1 amp.
Would you work in SI units, so like kilograms and cubic meters, or would you normally just work in whatever's computed?
Your problem is that the relative atomic masses are in grams.
Okay.
That's periodic table data for chemists is always in grams. So you've got to use like for like. But the reason why I've gone down to microns is because in reality that's the sort of rates that you're dealing with. If you look up corrosion rates in millimetres per year, they're fractions of a millimetre per year, hopefully, unless there's something seriously wrong with your plant. Yeah, you're right. From a scientific point of view, you go for standard units, but in reality we go for things that are close to give us values that are typical of what we're going to find. So as long as you stick with like for like, you'll be all right. Actually, that's another point. Densities are usually in grams per cubic centimetre. I know that multiplies straight up, but well, yeah. kilograms per cubic meter. No, it
7,850
won't. Yeah,
kilograms.
yeah, yeah. So would you really want to take it up and then drop it back down? No. It'd come out with the same answer in the end, it's true, but I think it's easier to do that way. Okay. So, if you've got a 1 square metre anode, then you don't lose very much through section thickness for an amp flowing for 53 hours. If the anode's much smaller, say it's only 1 square centimetre, then the growth of the loss of thickness is much bigger, because the same volume of material is being removed from a smaller surface area anode. So the depth that's lost must increase. And this is an important point because it's exactly what we see in things like stress corrosion cracking. The surface area of the anode in a stress corrosion crack is tiny. So the rate of through section loss is large. So they're a ratio of each other, if you like, you know, an inverse ratio. Larger the anode, the slower the loss of through section thickness. Smaller the anode, the higher the loss of through section thickness. And that's part of the reason why general corrosion isn't a problem, particularly. But as soon as you get pitting or localized corrosion, it is a problem because you start getting failures much more rapidly. And there's an interest in the ratio of the anode to cathode process. Remember, the two processes occurring at equal and opposite rates. One of them's generating electrons, the other's using up electrons, and they have to balance. So if you've got a cathode of a particular area, then only so much oxygen reduction or hydrogen reduction can occur on there. There are limits because of the area of the electrode in contact with the solution and the diffusion of the species to and from it. If you have a small cathode, small anode connected to that cathode, then you're going to get quite rapid corrosion of the anode. If you have a large anode, then it's going to be much slower in terms of loss of through section thickness. The actual corrosion rate in terms of volume of material should be the same, but one is losing much more through thickness than the other. And in the stress corrosion case, you have a large cathode external surface and a small anode. And the same effect happens in galvanic corrosion. The ratio of the anode to cathode is quite important. And so there's, if you're looking at sacrificial anode systems, there's a calculation done for the size of the anode that you need and how long it's going to last. In comparison to, because generally the anode is small in the cathodic protection system, in comparison to your structure, which is the cathode. Okay. Let me just check. in a sense, what we're more interested in is the current density, the current per unit area flowing through the material. And so there are lots of things that influence the size of that current density. So how much of the structure is exposed to the environment? Are there coatings, paint coatings on it? Are there passive films on it? What is the throwing power of the electrodes, the anode to cathode, if you like, the fall off with distance of the current? So are the anode and cathode close together, or are they a long way apart? The size of the potential difference between your anode and cathode, because that will have an effect on the magnitude of the current, because it's just an Ohm's law thing. Yeah. The current is the voltage over the resistance. If the voltage is high, then you get more current, and similarly, if the solution isn't very conductive, if the resistance is high, you get less current. And that's one of the reasons why when you go into closed loop systems, into power station systems, they tend to use low conductivity water with a high resistance. So that reduces the amount of corrosion current. So, although the Faraday's law calculation just looks at current flow, total current flow through the anode, really in terms of loss of through section thickness, you begin to start thinking about current density instead. Okay, that's a good place to stop. Thank you very much. See you next week, and we're in Cassie building next time. Oh, you're right.
At the beginning, I was saying regarding one book. I mean, if I'm not wrong, yes.
There are a couple of books, but
One, just easy one.
Denny Jones, Corrosion.
I couldn't find this one. Benny Jones. Yes.
Yeah, D.A. Jones.
E.A.
D.A. Jones.
Jones.
Oh, so go on, I'll write it down. There were certainly copies in the library when I last checked, but that's a couple of years back, and I can't believe they would have thrown them out.
I was looking. Actually, I was looking online. So.
Yeah, borrow a copy.
This is corrosion.
Corrosion control, I think it is. Was it corrosion prevention? Actually, I'll have it on here. Hang on. Principles and prevention of corrosion.
Do they have this kind of explanation there, like galvanic?
Yeah, he's got the corrosion mechanisms. His explanation will be slightly different from mine, maybe, but because he has more time. But yeah, the principles are the same. All I'm saying is my notes are not just complicated. So I'm trying to sort of summarise and give you okay, yeah, good book. Cheers.
The refinery. No, I get it.
Doesn't like chocolate.
Refinery.
맛있던데 근데
Cheers now. See you again.
형님 그린 라인 센트럴로 와야지. 이게 뭐 이게 어디로 와야 돼?
No, let me test your shot.
녹색 노랗게 다 오는데
딱 보이네?
이거 맞은
So we are not absent today, yeah? We are absent today. Has he replied you? Yes? Yes or no?
No, but now he's talking about now.
Same reply.
The same for everyone. Yeah, someone.
Reza.
It's
Angus. Focus. Imran. How are you?
I think it was better actually you didn't come yesterday.
Seeing Shahrukh and his punches, it's
Story is a press man. No. Story in this, you know, what he first thing he's so poor, and he thinks business is life. Then what he does for business and what happens when he goes over. That is story. Story is the best. But the not much expectations. The theater sucks, man. What theater is? Screen the seating capacity will be like this. The screen will be like this. Small. Moses. Class is over.
young bro, kid
I have
bro.
insomnia. I couldn't sleep all night.
Why?
I'm not sure it's work.
So put on.
What's 30 minutes?
before and after.
Before and after, no. They said before and after.
After, yes.
I think it's there, yes.
20 minutes before the end of the class.
Yeah, and after such a way.
No.
End of the class.
30 minutes before and 30 minutes
That's why it's not
before
open
the
for
end.
you.
Before the start and before the end.
Before the
Yeah.
start and 30 minutes.
Try it,
before
try it.
the
You have
end.
even forgotten your smart card. You don't have your smart card.
Everyone forgot.
I go.
Kid bro.
You also forgot?
So, skill needs. That's a problem.
Yeah, same.
Because